Alright, so today we start with our tangent function. And before we can actually start looking at what the tangent function is, I'm just going to go over what tan actually represents. So if we go back and we say, alright, well, what was tangent? So what was tan? Well, it was equivalent to the sine of theta divided by the cosine of theta. So as you can see, we're going to get one function in terms of two other functions here. And because we've done restrictions at the beginning of the year, we know that there's going to be some sort of a restriction because we have a rational type of function and our denominator cannot be equal to 0. So if we go back and look at our trig circle, we obviously know that we have our four quadrants. And now we ask ourselves, okay, well, if cosine of theta cannot be equal to 0 because this is your restriction on the denominator, when is cosine of theta 0? And that happens twice. It happens at pi over 2 and it happens at 3 pi over 2. So if we were to look on our trig circle right there and at the top. So in other words, we have two restrictions at pi over 2 and 3 pi over 2. So tan of theta does not exist if theta is going to be pi over 2 or 3 pi over 2. This is what it's telling us. So in other words, we have a tan function. It's going to be written in terms of sine and cosine, but the cosine of theta does not equal to 0, so tan of theta cannot be equal to values when theta is equal to pi over 2 or when theta is equal to 3 pi over 2. It's undefined, in other words. So what does this mean? Well, if I were to set up a graph, we would end up with vertical asymptotes. And where would these vertical asymptotes be? Well, at rotations of pi over 2 and 3 pi over 2. Now it's also logical to say that if instead of going counterclockwise on my trig circle, I would go in the clockwise direction, well then I would end up with asymptotes in the negative pi over 2 and negative 3 pi over 2 as values of theta. So on our graph, this is going to be for the basic tan function, we see that we have our asymptotes, and our asymptotes are spaced by periods of pi. So this should give us an indication what the actual period of the tangent function is. And in reality, it is pi. And this is only for the basic tan function again. So this is what our basic tan function will look like. Now, how was I able to graph these? Well, all you need to do is start off and look at your remarkable angles. So at a value of 0, you had 0. And then if you were to start looking at pi over 4 and pi over 6 and pi over 3, you would be able to start graphing the values on this side. And the same thing with a negative rotation, and you would be able to start graphing the values on this side. Now notice very, very carefully that your period is going to happen between pi over 2 and 3 pi over 2. And from negative pi over 2 to pi over 2. So these periods are always going to be in terms of pi. So that brings us to the period being defined as pi. And our vertical asymptotes in this case are going to be pi over 2 plus pi n. So again, why am I adding a pi n? Well, I know that my first asymptote is going to occur at pi over 2, which is what we found before. And when am I going to get my next asymptote? Well, after one period, obviously. And what's a period? Pi. And what does the n represent? The amount of turns that you're doing. Your domain for the function would be all real numbers excluding the asymptotes. And in this case, because we have sort of a rational type of function, we can use the rational definition for our domain. So all real numbers excluding the set of asymptotes. So the zeros for your first cycle, which is in red. So again, I'm only looking at one cycle, one period right now from negative pi over 2 to pi over 2. Well, there's only going to be one 0. There's always going to be just one 0. So our basic tan function doesn't have a parameter a that's greater or less than 1, doesn't have a parameter b that's greater or less than 1, doesn't have a h, doesn't have a k. So in other words, it's just y is equal to tan of theta, or tan of x. But when we start moving this tan function around and we start playing with some shifts and vertical displacements and horizontal displacements, we now get the form of the tan function where we have a parameter a, parameter b, a h, and a k, just like all the other functions that we've done this year. So the period, what would the period be in this case for our tan function? Well, if for the other sinusoidal functions it was 2 pi divided by the absolute value of b, in this case it should be pi divided by the absolute value of b. And again, what's the reason? Well, your tangent function has a regular period of pi rather than 2 pi. And if we want to find our asymptotes, and I've called these asymptotes x1 and x2, that's all they represent. They're just different asymptotes, the first one and the second one. All you're doing is you're going to take the value of your h, so your parameter h, and you're going to subtract the period divided by 2, and you're going to add the period divided by 2. Now somebody might also just say, well, okay, I know what one asymptote is. I can easily find the other one by adding the period, or I could find the one that's previous to it by subtracting the period. Yes, of course you could. The problem is when we're going to be graphing, we're going to be looking for these asymptotes, the one before and after, that's going to tell you how big your period is. So, what are the steps for graphing? Well, the first thing I want you to do is locate the point hk. Then find your period. Draw the two asymptotes. Now, these are going to be dashed lines. Now, let's look if the a times b value is going to be greater than 0, or if the a times b value is going to be less than 0. If it is greater than 0, your function will be increasing over that period. If it's less than 0, it's going to be decreasing over that period. And the last step is to find and graph 2 points between the asymptotes. Alright, now I would choose one before the 0 and one after the 0, but again, does it really matter? Not too much. You're sketching it. This is a very quick sketch. If I wanted a perfect graph, I would ask you to use a mathematical software. So, let's start with this example. So we get 2 tan half of x minus pi over 2 plus 1. Our period would be pi divided by half in this case, which gives us 2 pi. So that's the first thing we need to do. Then we need to find our h and k. So h and k in this case would be pi over 2 and 1. So pi over 2 and 1. So once that dot is actually represented, I now can start finding my asymptotes. And my asymptotes, we said, were at one side and on the other side of your h and k. And you're going to have to use that little rule that I showed before, the x1 and the x2, which is going to be your h minus the period divided by 2 and your h plus the period divided by 2. So we get our two asymptotes. Now that's fine. Let's move on to our next step. We know it's going to be positive, so we're going to be increasing over our domain. So let's find the points. So if x is equal to 0 and x is equal to pi, let's see what happens. Well, with x equal to 0, we get a value of y is equal to 1. Make sure your calculator is in radians, everyone. And the same thing for x is equal to pi, and you would get y is equal to 3. Now, I suggest you work this out. Don't just take my word for it. Work this out. So you would plot your 2 points. And you would get something like this. Now, obviously, you would have to connect these, and you would need to connect them as a curve. Using my mathematical software, this is what my graph would look like. Now, if yours is not exactly perfect, that's fine, but this is what it should look like.